Let's talk about normalization. So we kind of just think up of wave functions. We apply bounds depending on what our system is. And then we have to do some other stuff to make sure the mathematics works out and make sure we get something realistic. The next section we're going to discuss is normalization. Let's say I wanted to find the probability of finding an electron and I integrate over all space. What would the value of that have to be? It has to be 1. In order for this to be true, it's expected that your wave functions are normalized over whatever range you're looking at. If it operates outside of that range, the math might not follow. Also, what happens when you consider infinities with functions? Or what can happen? Sometimes. There's also a lot of weird behavior once you start considering infinity. The real big turbo math nerds would be up in arms if you really started what's the limit of blah, blah, blah as you go to infinity. We don't want to deal with that. We want practical stuff. So we tend to set ranges. So the probability of finding a particle over all space should be what again? Yep, 1 or 100%. In order for this to be true, wave functions are expected to be normalized. Okay. Let's look at an example where we have an unnormalized wave function and we're trying to normalize it. We're actually going to use the same function that we used in the last example, but we're going to have no what's called normalization constant on the front. So example, assume that the wave function of a system exists and is psi of x is equal to sine, oh, I guess ours is a little different. Where x is the only variable. If the region of interest is from x is equal to 0 to x is equal to 1, normalize the function. Okay, to do this, what we assume is we have psi of x is equal to whatever our unnormalized wave function is. Times some constant. We give that constant the symbol n. What do you think that's for? Why n? Why not k? Yeah, that's the normalization constant. Okay. So we got psi n psi x star what will my d tau be? What variable am I going to integrate over? Yep, dx. What's my range going to be? Or my integration limits? Yeah, how do you know that? Yeah. Yep. So we're going from 0 to 1. And we know what the value of this will be. What will the value be? Yeah. But we got to find that n, that normalization constant. Okay, if you notice, I have the n in the complex conjugate portion here. That could impact things if there's an I. Well, let's see if it will. So we got 1 is equal to 0 to 1. And if I take the complex conjugate of our function, that thing, does it change at all? No. Times sine pi x over 2 times n sine pi x over 2 dx. Okay, can you simplify this for me? Yep. Yep. What's n again? It's a constant, meaning, right, because it's just really a number, right? So we can pull this guy out front. We get 1 is equal to n squared integral okay, what now? Yep, table of integrals. We're integral from, what was it? I have a definite integral. No, I didn't. dx was equal to that over 4. Yeah. Is that right? Okay, what's our b in this case? Yeah. Okay. So we got x minus 2 minus, what's the next term going to be? Yep. Yep. Minus 0 over 2 plus 1 over 2 pi. Oops, I guess I'm taking it right to the integration limits. What should these change to? Yeah. Sorry. Okay. What now? Yep, because math. Because sine of pi is what? Yep, sine of 0. So now you get 1 over square root of n times 1/2. What were we looking for here? The value of n, right? Okay. So, what would you suggest to do? Yeah, solve for n. Okay. What's n equal to then? Yep. Okay. So this is the normalization constant. Our normalized wave function is psi of x is equal to what? You can just go with square root of 2 because you want it to be, in reality, it doesn't really matter. Yep. Yep. And that's our normalized wave function. Before I let you go, what was the wave function that we had in the last example? What's that for? Mm-hmm. Now, let's say we went from the range of 0 to 2. We wanted it normalized over that. How would our normalization constant change? So we would get to this point. That should be, oh, actually, no, we'd have to plug different values in. It could change things up a lot. Right. But in this case, it'd be sine of 2 pi. Sine of 2 pi is it 0? Yep, that's right, because it's factors of pi. So then, okay, then it would work out the same in this case. But there are situations where it would not. Okay. So do you feel like you understand what wave functions, the requirements of wave functions, and you get what normalization is? Okay. You'll want to be able to do that pretty flawlessly and understand what those things are going forward. Next time, we're going to talk about observables, something called orthogonality, which is awesome. It makes a lot of complex math just turn out to be zeros and ones. And we'll talk about Hermitian operators. This class and the next class, you really want to be sure to get that foundationally correct, have an idea of what's going on, and try other examples beyond the daily problems. If you can do that, you're like set up for the rest of the semester. Okay? Any questions at all? I know you got to run. So I forgot that we have the students doing calculations in Gen Chem. So this week we're going to meet to talk about the carbon nanotube lab, but they're going to be calculating things for the next 2 weeks. If you can try to calculate stuff outside of the hours of 1 to 5, that would be fantastic. We will delay everything 2 weeks. Okay? Till they're all done. Any questions about that? No? We should be able to run stuff for the carbon nanotube lab. It shouldn't take too long. Your MAO stuff, though, is probably going to take a while. So check your calculations, see if stuff is running. If it's still running by 1 o'clock, I will have to kill it today. Okay? But you can always restart them. Does that make sense? Okay. All right. Have a good day. I'll try to send you an email, too, if I kill your stuff.